to the extent where there are very few questions in the book about it, and the first year they added it in, it took a lot of people by surprise because they hadn't seen a question like it before, and then it suddenly just appeared in the exam. So, to not take you guys by surprise, we'll go through it and we'll do a couple of past exam questions, and then there's actually one more thing that I forgot to write notes on here for, but we'll do it on the back page. Alright, I guess before starting it's worth recalling a few things. Firstly is how we transform functions. So you guys might remember this table from last year. Those in my class will have seen it. But it's reminding ourselves that if we have a plus or minus on the end, that's translating up and down, plus or minus inside, you're going left or right. Many of you guys will use this in your investigation. Negatives, flip it. Whole numbers out the front or inside have vertical or horizontal dilations. Also, it's worth remembering the log laws, or the 3 key log laws, that I could have typed out nicely, but instead I got a screenshot of someone else writing it by hand. Alright, so, how do these things combine to a function of ln x? Let's just consider ln x versus ln 3x. Did you guys want to grab a calculator or just watch it on the screen? Alright, ln x we've seen before, it looks like this. ln 3x is that. Now what's the relationship between the two? Well, it goes something like this. If I have ln 3x, that is the same as ln x plus ln 3. Because under the log law, you can split a multiply into an add. So the relationship between ln x and ln 3x, strangely enough, is a vertical translation of ln 3, meaning this blue graph is ln 3 above the red graph at any one point, which is neat. So we're using log laws and what we already know about transformations and applying it to the graph. If we did this without a log law, there is another interpretation. We're just replacing the x with a 3x. And if I jump back to this, if we put a bx in there, there is a horizontal compression if b is greater than 1. What it means is that any x coordinate gets divided by b. So in our case here, when we go from x to 3x, it means that any x coordinate here gets divided by 3 for here. So, probably an easiest place to see it is, you see how 4 divided by 3 at the same height, that will be about 4/3. So a bit over 1 1/3. Or here, what is that, 9 to about 3. So any x coordinate gets divided by 3. A much easier way in my head to think about it is a vertical translation of ln 3, because that's just a straight gap vertically up of ln 3. But there are two interpretations here, whether you apply the log law or if you haven't. Alright, what about ln of x squared? Now, ln of x squared, there's really only one interpretation. You have to use the log law. ln of x squared is the same as 2 ln x. What's the impact of that 2 if we're going from just ln x to 2 ln x?
Is it a vertical stretch?
It is, it's a vertical stretch. So we are doubling every y coordinate. So if we have ln x and ln and 2 ln x, we double the y coordinates. Doubling 0 is still 0, so we're expecting that. But where this one was, what? I'm trying to pick a solid point. Where this one was 2 and a bit, it turns into 4 and a bit. Where it was 2 1/4, it turns into 4 1/2. So there is a doubling happening vertically. So So that squared by log law at the front gives us a way we can interpret it. And it would be quite reasonable of them in the exam to ask what is the relationship between ln x and ln x squared. And the relationship is ln x squared is a vertical dilation by a factor of 2, or a vertical stretch by a factor of 2. Alright. So, and that probably leads down here. The impact of A in this case is a vertical translation of ln A, meaning we are moving up ln A. Or in this case here, it's a vertical stretch or vertical dilation of a factor of A, because that A will drop out the front, doubling the original ln x. Okay. So from there, let's look at what these people saw in exam. And this, I think, was a little unfair in the exam. Some teachers won't have picked that they added this to the course when they originally added it to the course, and therefore this question will have just come out of the blue. Alright, so on the graph below, you're shown two graphs, ln x and ln 3x. And they've asked you to show that p-x is equal to q-x. So do you guys want to have a show of that? I'll do it on the board as well, but I feel like you guys can probably do that. If p of x equals ln x, p-x is 1 on x. If q of x is ln 3x, q-x is 1 on 3x times 3 equals 1 on x. Importantly, in terms of making sure you're picking up the exam marks, it would not be a good idea to leave that line off. If you've just done ln x is 1 on x, and therefore, oh, show they're the same. Yeah, sure, q-x is 1 on x. That's not communicating you know how they've got to the same place. That's just finding one answer and making the other answer the same because you kind of want it to be that. You really do need to show where the threes go. So part of this is communication. You need that line for the mark. Because they've told you the answer, really, but they need you to communicate it. All right. Describe the relationship between px and qx. And this is where that log transformation helps. So, I would say that qx is px vertically translated by ln 3. So it's ln 3 up.
Did you just write that in rows?
Yep. So words. So if you want, you can say that qx is equal to px plus ln 3. But then you do need some words. You need to say that this qx is a vertical translation by ln 3. So qx is px ln 3. All right. Consider the function Rx, which is ln x squared plus 6x plus 9 with a domain of x is greater than -3. And we've got the original ln x, which is px, and we've got our new Rx floating out there. Rx can be written in the form of a ln x plus b, where a and b are positive integers, determine a and b. ln x squared plus 6x plus 9. Now, this is our starting point for Rx. Can anyone sort of see something suspicious or familiar vaguely about that?
Perfect square.
Nice, it's a quadratic, and it's a special kind of quadratic. If we're looking for things that add to 6 and multiply to 9, it's 3 and 3, it's a perfect square quadratic. So this is really the ln of x plus 3 squared. Yes, so you put the square at the front. So this is then 2 ln x plus 3. Here, and this is another mean one. If you got there, you're probably getting one of the 2 marks. A really frustrating way to lose the mark here is not actually answer the question. They've asked for A and B, so give it to them. A equals 2, B equals 3. That would be an annoying place to drop a mark, because you definitely feel like you've got it, but you actually need to tell them, what they're after. Cool. Hence, describe the relationship between the graphs. So, we've done a bit of math. What do the 2 and the 3 indicate? Yeah, we can flick back to page 1 and we're like, okay. Good. 2 is vertical stretch or dilation, and the 3?
Horizontal translation.
Good. Horizontal translation, left 3. Hello.
Hi, sorry, have you got Ben in here?
We do.
We do. Got a base
So, the language we're after here is Rx is Px translated 3 to the left, and you can see it goes from 1 there to -2 there, so 3 to the left, and then stretched vertically by 2, so doubled. When you can see that this point doesn't get stretched at all because it was 0 high and it's still 0 high, but this point here would have been moved across and then across 3 and then doubled.
Sorry, what was the sentence?
Oh, sorry, the sentence is translated 3 to left, or you could say translated horizontally by -3, something to that effect. Then vertically dilated by a factor of 2, or vertically stretched by a factor of 2.
No, it's stretched towards either.
Yeah,
It's stretch, isn't it stretch, it's like, it's stretched and dilated, so.
essentially, yeah. Stretched is only bigger, dilated depends on the factor. So dilated factor of 2 or dilated factor of 1/2 will both work. As long as you're clear about what you're saying, you'll get the 2 marks there. Okay. All right. Now, that is the end of that example. I don't think I printed another, was it? No. On the back, though, you've got a blank back sheet.
Yeah. Oh, yeah, you get the box. Like no work. You find you go. Can you get a box?
All right. Now, log laws can also be used to help with differentiating. It's one of those cases, so this should be on the blank on the back side, sorry I forgot to write it in. This, and many of this type of case, is one of those things where you can either do it an easy way or a hard way. So, Here, pick the easy way. Really, you've got three things multiplied by each other. If you were going to do it the hard way, you would make this as 1 on f of x multiplied by f dash x. And then you would be using product rule to find that, and it turns into a bit of a mess. So rather than doing it the hard way, I would recognize that this is the same as ln2 plus ln x plus ln e to the x. Log laws work out like that. Then, if we're going to differentiate it, f dash x, ln2 is a constant. It differentiates to 0. ln x, by definition, is 1 on x. This, are we happy if we throw the x to the front? And then we have ln e, and ln e is 1. So really, it's worth reminding ourselves that this entire thing is just equal to x. And if we differentiate it, we get that. So rather than using 1 on f of x and then multiplying by the product rule, this makes our life way easier. So we should, every time we should see a log, before differentiating, you should think, can I use log laws just to make my life nicer? We'll do one more. The one more is g of x equals 3x squared plus 7 over, the natural log of, otherwise the whole question doesn't work. ln 3x squared plus 7 on 2x to the power of 4. Good, it's a take. So this then becomes ln 3x squared plus 7 minus ln 2x to the 4. Now, it's probably worth not getting too excited. We can't split the plus. It needs to be a multiplier for us to split it. And we could split this, there's not a huge benefit to it. So now we are actually going to have to do each separately. This is going to be 6x over 3x squared plus 7. And this will be, still minus, 8x3 over 2x4. And then clearly there's some simplification to happen there, but that's fundamentally where we're going. So, several parts today, log transformations using log laws and transformations, and reminding ourselves that when we differentiate, it helps enormously to use a log law first and then differentiate. Sound good? All right.